Hello and welcome to Falling Walls Breakthrough Conversations. This is a safe and quiet space for interaction with global leaders, outstanding scientists, emerging innovators and science entrepreneurs looking at their individual research, career paths and experiences. In the audience, you're very much encouraged to interact with our speakers and to actively participate in the discussions. I'm Nicola Jones. I'm the Head of Publishing for the Springer Nature Sustainable Development Goals programme. And for the next 25 minutes, I will be talking to Eric Isaacs, who is the President of the Carnegie Institution. A couple of technical details before we start. So for the audience, in order to communicate with us, please use the raise hand function on Zoom, and you'll be spotlighted and unmuted, and then I'll invite you to ask your question. If you have a follow-up, please raise your hand again and the same thing will happen. For any technical questions, please enter those into the chat and one of our moderators will get back to you. This conversation is being recorded and it will be available on the Falling Walls content library after the Science Summit's completed. So let's meet Eric Isaacs. Eric is a condensed matter physicist and the 11th president of the Carnegie Institution for Science, which is a private, non-profit research organisation based in Washington, D.C. As president of Carnegie Science, Dr. Isaacs leads the institution's investigators in forefront research in plant biology, developmental biology, earth and planetary sciences, astronomy and global ecology. Now, thank you for joining us today, Eric.
It's a pleasure to be here. Thank you for having me.
So given your focus and the focus of the Carnegie Institution and indeed Falling Walls on breakthrough research and your participation this afternoon in the Circle plenary table on transatlantic cooperation, perhaps we could start by talking about what are the topics that you think global cooperation is most needed for at the moment and, what more needs to be done.
Yeah, that's of course that's the trillion-dollar question. Certainly, climate change is in my mind, it's the big one. That's the one that's going to affect everybody on the face of the earth, and in some areas more than others. Obviously, we've been through the pandemic. We've seen how global cooperation is critical for that. So, for example, between Pfizer and BioNTech, which is here in Germany. So I would say the top line, and we can talk about any part of science that you want to, like astronomy, astrophysics, the stuff we do, but I do think that climate change, the ecology, the environment is everything. It's about human health, it's about environmental health, it's about water, it's about food. So in my opinion, that's where global cooperation is absolutely the most essential. Certainly from the point of view of how it affects the world, is anything done here in Germany, anything done in the United States, is felt all over the world. Climate is a global problem. It's very different than, say, local issues of water, but it is a big problem. And so I would say that's probably the most important problem to tackle today.
And so if I might ask a follow-up to the trillion-dollar question, how do we need to do better to tackle climate change?
Yeah. Well, first of all, I'm a physicist, as you've pointed out already. And it's oftentimes true that scientists figure that they can solve any problem the world has. And okay, I'll take that credit. But in reality, this is not just a problem of scientists, obviously. This is not. There are real science problems that underpin climate that are involved, for example, in energy, which is inextricably linked to climate, as we know, the use of energy. And certainly as countries like Africa start coming up, to more economically viable types of places, it's going to be more and more the case that we're going to need energy. So energy, obviously, is at the core of climate. But scientists, as scientists, we can solve a lot of those problems, but in the end, this is not a science problem. This is really much more of a collaborative problem between scientists, politicians, even humanists who can write well, who can communicate well. My colleagues in science are fantastic people, but in the end, we really need to think about how we put together a much broader range of not just disciplines and research, but a much broader range of people to figure out how to do this.
So I think it's really interesting that you've mentioned that this is not purely a science problem and different sectors need to work together. And you also mentioned Africa in your answer. Does more need to be done to ensure global inclusion? We're talking about transatlantic partnerships, but actually, do we need to do more to encourage participation in these conversations from people who are in places that maybe will be more affected by
Yeah,
climate change.
Absolutely. And actually, that is a role that scientists can play, because scientists tend to be extremely collaborative. And there are opportunities right now in Africa, for example, or with China, which may be the $10 trillion question. But there are certainly opportunities for scientists to collaborate across all those spaces to create that kind of connection. But there are things we can do much more effectively with places like Africa. I mean, economic is the big issue there. So, I mean, their economic stability, that has to happen. And I don't expect that Africa is going to be investing the kind of money, say, here in Germany in science. But that's where collaboration can be really highly valuable.
Do you have any examples of, I guess, projects or collaborations that the Carnegie Institution's been facilitating here?
Yeah, so we have in particular anywhere, or just transatlantic? Are you talking about
transatlantic for global challenges?
Yeah. Well, as we mentioned before, climate change is a global challenge. We all know that, and our scientists are extremely interested in understanding ecosystems that vary across the world. So we are working actually in places like the Arabian Sea. We're working in Australia. We're looking at coral in Australia, where you can call coral the canary in the coal mine. And actually, this is a good place where science can play a role. It's not just policies and politics. If you look at coral, which is of course disappearing, as we know, across the world, understanding. So we understand that when the waters warm up or they become more salinated, the coral bleaches. But understanding that the biology behind that is something that we don't have yet. So we're just starting to understand that and figure out ways to mitigate. So we have scientists who are trying to understand the genetics behind. So instead of thinking about human health and trying to study human health with genetics, we're about trying to study environmental health using genetics, looking at the symbiosis between different species in the waters, for example, around coral. So that's everywhere in the world. It's in the Arabian Gulf. That's in Australia. That's everywhere. So we see science very much as global at Carnegie.
That's really clear from the answer you've just given me.
Yeah.
So just to follow up from that, could you maybe tell us a little bit more about your background and how you came to this this role and this interest?
Sure. So I think I've had almost every kind of role in science you can imagine. I started as a condensed matter physicist, as you said, at what's called Bell Laboratories, which it's one of it used to be one of the premier labs back when industry was running a lot of really important labs. It's a little less so now, and we can talk about why. But from there, so when I was doing work there, it was the best job I ever had in some ways. It was basic science, but it was also basic science in the interest of a mission, and the mission, of course, was communications. So you could work on things like superconductivity. You can work on optical fibers, fundamental science, molecular physics, atomic physics, all with an eye toward 20 or 30 years down the road, doing something important that would scale. And scale isn't important, because I'll come back to climate change in a minute with scale. I then moved to Chicago, where I was a professor of physics at Chicago, and eventually became director of Argonne. The reason that was great, Argonne National Labs is a Department of Energy laboratory, much like DAISY is here in Germany. It's a national laboratory for general use, actually for anyone in the world to use. But it also was part of the Department of Energy's portfolio of laboratories with the purpose of trying to address the energy challenges. Again, they're doing basic science in the interest of long-term gains in energy. So, for example, building a better battery. And building a better battery, we have batteries. You and I are using them in our microphones, in our watches, and in our phones. But there's still a lot of work that needs to get done. However, I would say, like many things, batteries, we kind of know where batteries are going. It's not an unknown, so to speak. We kind of know where they're going. But that kind of work, doing basic science in the interest of this sort of long-term impact, is ultimately what I have sort of gravitated toward. And that brings us back to climate change, which, again, I think we know a lot of what needs to get done. This isn't, some people say, rocket science. The challenges are huge, and the big challenge in this is scalability. So one example I like to use is the carbon problem, right? And fossil fuels aren't going away. We're going to use them. And if you think about how much carbon we're putting into the atmosphere on an annual basis, we understand the science. I mean, you burn fossil fuel, you put carbon in the atmosphere. This problem, how we address that, is real science, and the reason it's science is scale, and the scale is really something. So just a few numbers, because I like numbers. If you look at the amount of carbon we're putting into the atmosphere now, that's human-made, it's about 40 gigatons. That's a big number. 40 billion tons. It's a very big number. In the atmosphere, there's naturally about 700. The Earth breathes carbon, so through carbon cycle, through the oceans, through the trees, et cetera, photosynthesis. But we're putting up about another, call it 10%, 5 to 10% a year into the atmosphere. And that's a lot of carbon, right? And that's why we're seeing what we're seeing today. You could say, well, let's try to capture all that carbon. You've heard of carbon capture and storage, and that's everyone's talking about it. But the scale of the problem is what makes it interesting, or challenging, however you want to look at it. If you take the chemical industry all over the whole globe and you ask how much chemicals are processed every year by people, by humankind, it's about a half a gigaton. So the problem is 100 times bigger than anything we even can conceive of today. And so when people say, well, let's just sequester the carbon, I'm totally in favor of it, but it is a really big challenge. And that's not going to be solved in the US, it's not going to be solved in Germany, it's not going to be solved in the UK. It's a really grand challenge. And that's the kind of challenge which I think brings scientists, but also it's got to bring more than scientists, got to bring politicians together with scientists.
And how do you see that kind of cross sector, if you like, communication, collaboration, facilitation working? Where are there opportunities, let's say, for scientists to work more with politicians?
Yeah. So let's start just with the scientists, because it's a challenge, right? This cross professional or cross-disciplinary collaboration is very hard. So even start within the sciences, a problem like carbon capture, it's chemistry. I mentioned chemistry because you have to somehow take the CO2 and make it into, not a gas, but into something that can be stored, or like rock, like calcite or something. And then, so that's chemistry, but then you also have to, the scale is earth science. I mean, it's earth system science. So you have to have geologists, geophysicists. It affects the biology. I mean, the Earth's evolution, 4.5 billion years of evolution, is all about this inextricable link between the Earth, the carbon, life itself, right? And all this interaction. So you need biologists. You need to understand what the impact of all this could be, what the impact of the carbon is. And even within the science disciplines, that's been a challenge. So the first thing I think that has to happen is we have to look toward much better interoperability amongst the disciplines. And a lot of people say this, I'm not unique in saying it. We speak different languages, so the first thing is to get a vocabulary straightened out. But I think a lot of it is just, and it comes back to now let's get to the next level up, not the political side, but the funding side. It's really important that that we start thinking about funding these projects not as, I'm a physicist, let's fund you to do a little bit of, think about, geophysics, and fund some chemists to do something separately. I think we need to think about how we fund these groups to attack problems. Getting back to Bell Labs, what Bell Labs was like was a place where you had chemists, physicists, biologists, all working with the big mission of communications. We need to do a similar thing there. We need to have, I think, a way to think, rethink a little bit how we fund basic science projects.
I'd just like to remind the audience you can ask any questions at any time by using the raise hand function in Zoom. So let's go on. As head of publishing for the Springer Nature Sustainable Development Goals programme, I spend a lot of time thinking about how we can get research that has the potential to address the goals or help achieve the goals by 2030 into the hands of people who can use it, which has a lot to do with what you've just talked about. I'd like, therefore, while I have you, to ask if there are ways that you think publishers and other organisations that sit on the periphery but integrated with the science system can help to facilitate that. Yeah.
Well, what you're doing right now, of course, is part of that, right? I mean, you are talking to a range of people interested in probably this very same problem, right? So I think that's a big help. I do think a lot about this, and I think it's multi-pronged. So first of all, scientists themselves need to be taught to be better communicators. So we tend to get very detailed, technical. Scientists tend to do I did this, we do this, and then a miracle happens. Instead of starting by saying, if we could do a few things, we would be able to, we'd be able to handle 30 gigatons of carbon a year. And so I think you, as a journalist or, in media, can help teach scientists how to better communicate. What is it that, how do you present a problem to somebody? And not to subvert the science at all, but how do you make a problem interesting, exciting, but compelling to someone? I mean, to me, it's pretty compelling to say we're about to ruin the one planet we have. But I still think it needs to be made compelling. It needs to be humanized. And so I don't think scientists have enough, do that enough. This is not a negative comment about my peers. It's just that that's not a priority for us. And for example, in graduate school, it's just not a priority. So it might be that every grad student has some lessons in this. So that's one thing that certainly can happen. But the other is you shouldn't be on the periphery. I mean, journalists. I mean, I talked about politicians, but it's not just the funding. It is important to have people in your business who understand or gravitate toward the science. And I'm not sure how many do that. I've just a few weeks ago met with someone for the first time. His name is Joe Palca. He does a lot of news, like you do. He does radio and TV. And he's just like a kid in a candy store when it comes to science. So I'd love to see more people like him or like you out there having those kinds of conversations with the scientists, and then getting the scientists to report out in a way which is easy to understand. And I don't think that's quite happening yet. And I'm not saying you're going to change the mind of 40% of the world, but just getting truth out there is so important. And I think basically it is a lot about the communications. In fact, as president of Carnegie, I think about communications probably. If you ask me, if I have a 12 or 14-hour day, how many times a day do I think about how do we communicate this? It's probably most of the day. So it's a really important piece of the puzzle, and I don't think we've addressed it really well yet. So
it's interesting that you mentioned changing the minds of 40% of people.
Yeah.
We're also aware that there's a sort of tension and a skepticism often in lots of quarters that's impacting maybe the will of politicians.
Yeah.
To move towards this. Do you have anything to to talk about here?
No, it's a great question, and I'm from the U.S. and we're sort of struggling, like many countries, we're struggling with this right now, where truth is not necessarily the coin of exchange, so to speak, and it is a real problem. But I think regardless of that, we have to get out there and just keep speaking the truth. But we have to speak it in a way where it's not just for your peers in science, and you have to convey it in a way which is not just that as well. So in the face of, I'm not going to argue that I know enough to be able to change people's minds like that. I mean, I think the key is to just keep communicating the same message over and over again. That's another piece of thing that I'm sure you learn, right? Certainly marketers have learned that you tell something to somebody once and you got to say it again, and you got to say it again, you got to say it again, and eventually they'll hum the same jingle that you're humming. And so I do think communicate early, communicate often is really important. Maybe that's not an answer, but I'm just telling you because I just don't feel like I'm qualified to say, how do I change a person's mind? Are you ever going to have more than 40 or 50 or 60% that really believe in some of these big challenges? I don't know. And you would have thought that the pandemic would have had that big an effect, right? The fact that people see, that you had, first of all, international cooperation. And I mentioned Pfizer and BioNTech, which is right here. That is phenomenal, right? And that kind of cooperation. I mean, Pfizer basically was able to scale something that BioNTech invented. It couldn't have happened any other way. You'd think that seeing that, people would say not only is international collaboration important, but so is science. There's one other thing I'd add to this, though, which I think is really important, and we'll probably discuss this afternoon, is there's a natural and not unhealthy sometimes tension between competition and competitiveness, national, say, competition and competitiveness, and the need to cooperate. When you talk about the pandemic and you talk about climate change, we have to cooperate, we have to collaborate. And scientists are doing that, actually. But there is a need, countries do have a need to compete too, and it's not necessarily, although it often ends up being at the expense of others, but there is a need for any individual economy. Here in the EU, You see that this move toward the EU has been a very powerful, I think, standard of living for everyone in the EU has come up. But then there's the competition between the EU and China and the EU and Russia. You can name. There's also got to be cooperation with Russia. There's got to be cooperation with China. So the question really for me, and I don't have an answer. Maybe this is. I don't want to just throw it over the fence. Say it's for politicians. I'd love to have the conversation. How do we think about cooperation and how do we think about competition? And those two things, I think, both have high value. I mean, the competition does spur people to do better things, but the cooperation also spurs you to get to solutions faster, like with the pandemic.
I think that's a really important point.
Yeah.
So we have a question from the audience. If you'd like to go ahead and ask Eric.
Hi, hello, Eric. Thank you very much for the talk. It was it was a great pleasure to listen to you.
Thank you.
I wanted to ask a question. So I have two younger brothers, and my question is, how would you talk to the youth about science? So they're very curious by nature, but they're not very interested in science, and sometimes I try to kind of share maybe some books with them or some educational videos and stuff like that. But you as a physicist, maybe you also interact with, I don't know, teenagers and children. Maybe you have some advice for me, or actually also any book advice is also appreciated. Thank you so much.
That's a great question. So I mean, so I could ask you, how did you become interested in science? I'll tell you about me, not to be egocentric here, but the thing that got me into science when I was a young kid was astronomy. So for a lot of kids, it's the wonder. That's what you're saying. There's this wonder of the unknown, and we're talking here a lot about climate change, which in itself compels you, but it's sort of a negative. But if you talk about the incredibly interesting features of science, like, is there life on other planets? That to me is one of the most interesting questions you could ask. So I always find when I talk to kids, my kids are now grown in their 20s, but I talk to them. By the way, neither of my kids are scientists. One's a political scientist, economist. The other's actually a social worker. So both in the U.S. But when I talk to kids about science, I try to find the topic that's pure science, that's exciting. So it could be biology. Biology is one. How does the brain work, for example? These are big, grand questions. Or is there life on other planets? Or where did the universe start? Like, where did the elements that we're made of come from? If that's too esoteric, then you can talk about climate change. But I always look for, this sort of pure wonder in kids, and I find astronomy is one of the best hooks that there is, because kids just love this idea of where did all this happen? It's just sort of, to me, it feels almost like an innate quality that people have, this curiosity. That's what I do. But of course, I'd love to meet your younger siblings and find out what they're interested in. But it's a great question, and I think it is the most important question, is how do you get kids excited about science?
Thank you. I think the theme of communications come to you very strongly from our conversation today, and it ties in with what you've just been saying. Keep talking about it.
Yeah, and I think it's interesting when you look at K through kindergarten through 12th grade, which is, it varies a lot around the world. Excuse me. What you often see is that kids at a very young age are very excited about science. So take a kid in, a 10-year-old kid or whatever grade that is, third grade, third grade. There's this tremendous excitement about science, and often it's the most exciting. I mean, they'd rather open a book on the universe than open a book on literature and try to learn how to read. So the images, the pictures that really stimulate kids. But seems to be happening is as kids get later and later in their education, they lose interest in, they can say it's math, they can say it's science. And I think that is another area that's very important, is thinking about what a professional would call a pipeline, but how do you keep kids excited by science? So not just so they go into science, but so that when they're 30, 40, 50, 60, they're interested in hearing you talk about science, and they want to know, we have roughly monthly what we call capital science evenings, where it's all virtual now, of course. We just pick our own scientists or scientists from around the world, and we let them go for an hour, and it's designed for the public. And we found the virtual world is much easier. we're getting thousands of people who show up and just because they're curious about life on other planets, or they're curious about things like, why is coral bleaching, and how do they co-evolve with, the algae and the corals, which co-evolved to be symbiotic? How did that happen? People are just interested in that, and you find that there's a lot of people interested, but there has been this tendency that kids lose interest as they get into more senior years, and frankly, I understand that, from the point of view of what they're exposed to, right? I mean, it's social media, and I think most kids want to start a company or a game or so. A lot of kids, not most kids, and so doing that, it's certainly in places like Germany, there's less of that scientific side. I think it's more of what they're exposed to, which is more of the, let's call it the computing and digital side, which is nothing wrong with that, but it would be nice to have more science.
Thank you. Thank you for your insights today. Thanks for sharing your journey as well. It's been a really interesting conversation. Thank you to our audience. I need to wrap it up now. So we will be back in 5 minutes for the next Falling Walls Breakthrough conversation. If you'd like to stay on the Zoom, please do. Eric, thank you very much for joining us today, and I hope you enjoy the table this afternoon and the rest of the conference.
Thank you very much for having me.